This video is over lesson 91, effect of scaling on perimeter, area, and volume. So ladies and gentlemen, to kind of illustrate this and hopefully give you a visual for what's going on, we're going to make a series of figures here together. So the first one we're going to make is a square, and I want you to make your square just a single space big on your paper. So it's one space by one space, which means that its perimeter would be 4, and its area would be 1 times 1, which is 1. Oops, excuse me, equals 1. A equals 1. Now, next to that, we are going to double the size of our square. So 2 spaces big. So it's 2 on this side and 2 on that side. So a perimeter then, so 2 plus 2 plus 2 plus 2, or 4 times 2, perimeter then this time would be 8. And the area would be, well, 2 squared is 4. Well, we're going to go ahead and triple our original square now. So we triple our original square. 4 times 3 is 12, so perimeter is 12. And area is 3 squared, or 9. And then finally, we're going to do one more here, and we're going to quadruple our original square. So 4 here, 4 here. So 4 times 4 is 16, so we have a perimeter of 16. And then 4 squared is also 16. So if we take a look at what's happening here, perimeters. As I double my side length, my perimeter doubled. As I tripled my side length, my perimeter tripled. As I quadrupled my side length, my perimeter quadrupled. If we look at area though, when I doubled my area or my side length, my area didn't double, it actually quadrupled. When I triple my side length, my area becomes not 3 times as much, but 9 times as much. And then when I quadruple my side length, so 1 to 4, my area goes from 1 to 16. It becomes 16 times as much. And so, ladies and gentlemen, there's a certain pattern going on here where we've already kind of hit on this a little bit when we were looking at percent of change in dimensions, that when we change an area, our scale factor is going to be squared. All right, we're going to move this up now a little bit. And so we've got to come down the page a bit, probably skip about, I'd say about 5 lines or 4 lines. So 1, 2, 3, 4. And I'm going to make my little square again. But I don't want this to be a square. We're actually going to turn this into a cube. I'm going to go about halfway up the space and then connect it all. So if this is 1, that's 1, and that's 1 right there. And this is a cube, and so its volume is 1 cubed, or 1. Now next to that, I'd like you to make our double big square. So this time we're going to make it 3D by going all the way up 1 space with our diagonals. So if that's 2, and that's 2, and that's 2, well then volume of a cube is 2 cubed. That's 8. We do the same thing now with our square that was 3 times as big. So this time I'm going to go up a space and a half with my diagonals. And so if this is 3, and that's 3, and that's 3, then the volume here is 27, 3 cubed. And then last of all, Make our quadruple big square. This time we'll go up a full 2 spaces in the diagonal. So that's a 4, and that's a 4, and that's a 4. And the volume here is 4 cubed, that's 64. So as I double my side length, my volume goes up 8 times. When I triple my side length, so 1 to 3, this goes up 27 times, the volume does. And when I quadruple my side length, so 1 to 4, my volume doesn't quadruple, it actually gets multiplied by 64. And so again, like we saw in our dimensions, change in dimensions lesson, what's happening here is our scale factor is being cubed. So to put that another way, the ratio of linear measures is going to equal your scale factor, which is often symbolized as the letter K. So when we talk about linear measures, remember we're talking about lengths, which also includes widths and heights and radiuses and diameters, but any kind of length, even if it's not called a length, if it is a length, it counts there. Also, perimeter, which of course also includes circumference on a circle, because that is a perimeter. So that's our foundation. If you look at the linear measurements, that gives us our scale factor. So then the ratio of areas, so here when we talk about areas, obviously we mean area, we mean surface area, we mean lateral surface area, and so on, so on, so on. Anything to do with area, two-dimensional measurement. So since we're into 2 dimensions now, this will be your scale factor squared, or K squared. And then finally, ratio of volumes. When we talk about volumes, obviously volume, but also anything to do with capacity. So gallons and quarts and pints are all related to volume. So when it comes to volume, we are going to take your scale factor, and since it is a 3-dimensional measurement, you're going to cube it, or K cubed. So at this time, I'm going to ask you to go ahead and flip your papers over. No matter how much space you've got left, flip your papers over. And on the back, we're going to write practice. And so I'd like you to take your books and open up to page 613. 613, and we're going to work through the practice problems together. Hey, I'm not liking that line there. So if I don't like something, I erase it. All right, so practice A. If you know the scale factor between 2 polygons, describe how you can find the ratios of their perimeters and areas. So first of all, the ratio of their perimeters, oops, my I kind of blended with the M there for a second, of their perimeters is the scale factor. So remember, the ratio is the same the ratio of linear measurements is the same as the scale factor. However, for the area, the ratio of their areas, however, is the square. So we're going to square it, multiply it by itself. The square of the scale factor. And then if it asks us about volume as well, we would just say the ratio of their volumes is the cube of the scale factor. B. The dimensions of a wallet-size photo are about half the dimensions of a 5-inch by 7-inch photo. The area of a wallet-size photo is about what fraction of the 5 by 7 photo? Well, area, so a scale factor here, we're going down half the dimensions. So our scale factor is 1/2. Since we're asking about area, area is a 2-dimensional measurement, so we're going to square that. So 1/2 squared is 1/4. So what fraction of the area will it be? 1/4 of the area. C. A triangle with vertices 0, 0, 1, 0, and 0, 2 is dilated by a scale factor of 4. The area of the dilated image is how many times the area of the original triangle? Well, I don't even need to graph this out. We already know the scale factor, and we know we're asking about area. So scale factor, and it's 2-dimensional, so that means it'll be 16 times the area of the original. Oh, actually, you know what? For good measure, 16 what? 16 times bigger. Yeah, let's put that in. D. Find the scale factor of the smaller rectangle to the larger rectangle. Find the ratios of the perimeters and areas of the larger rectangle to the smaller triangle. So first of all, scale factor. So if we take a look here, I'm looking for corresponding measurements. So on the big guy, I've got 6 inches. On the little guy, I've got 2 inches that seem to correspond to each other. And well, inches and inches will cancel, and then 6/2 becomes 3. So the ratio of the perimeters, is going to equal, well, just same as the scale factor, just turn it into a ratio. So 3 would be like 3/1 or 3:1. And so then the ratio of their areas is going to be 3 squared to 1 squared, since we're going 2-dimensional here, which means this is a 9:1 ratio for their areas. So circle, circle, circle. E. Find the surface area and volume of a 1-inch cube and a 10-inch cube. What is the ratio of the surface areas? What is the ratio of the volumes? So here we go. I'm going to label this, start with my 1-inch cube. So it asks for the surface areas. Now surface area is nice on a cube because we have, well, each side is a square, so s squared. And then there are 6 of them, so 6s squared. So 6 times, well, I'll use parentheses actually there for times, because I've got 1 inch. I'm going to square it. So that would be 6 times 1 square inch, which would be 6 square inches. The volume of this, what am I doing? Equals, there we go. Well, it's a cube, so just S cubed. So 1 inch cubed, or 1 cubic inch. Now we need the 10-inch cube. So for my 10-inch cube, surface area then will be 6 times 10 inches squared, which would be 6 times 100 square inches, or 600 square inches. Volume would be my 10 inches cubed, which of course is 1,000 cubic inches. As for the ratios, we don't even need the rest of these numbers to find the ratios because we know the scale factor right there. So the ratio of the areas, surface areas, we know is going to be 1 squared to 10 squared, which will be 1 to 100. So, by the way, circle our answers here. So the ratio of volumes then is 1 cubed to 10 cubed, or 1, oops, got it myself there, 1 to 1,000. Moving on to F. One square has sides 10 centimeters long. A second square has sides 50% longer. How long are the sides of the longer square? So, well, right there, I'll just take a pause. So, the longer square is a 50% increase. That's a 50% increase from 100%. So if I find 150% of the 10 centimeters, that should be how long the side of the longer square is. So 150% is really 1.5 times 10 centimeters. Of course, if we multiply that by 10, it moves the decimal back over. So 15 centimeters is how long that is. So next up, what is the scale factor from the smaller to the larger square written as a decimal? Well, as a decimal, well, we just did it right here in our work actually. That's your scale factor. It's already decimal. And then finally, what is the ratio of the areas to the smaller, to the larger square written as a decimal? So as a decimal, the ratio of areas equals, well, that's going to be my 1.5 oh, sorry. That's going to be my 1 squared to my 1.5 squared. So the smaller one would be 1 compared to the scale factor 1.5. Square them both, and this is a 1 to 2.25 ratio. Now that ratio could work. Another thing we could do is we could multiply those both by 4, and so that gives me a 4 to 9 ratio. Now the book asks for a decimal, so I would give them a decimal. G. To celebrate her pizza shop's 10th anniversary, Blanca is offering double your dollar days. During this time, customers can get twice as much pizza for the price of a 10-inch pizza. What is your approximate diameter of a pizza? Twice the area of a 10-inch pizza. Assume the thickness of all pizzas is the same. Justify your answer. So we want to double the amount of pizza. So here's the thing though, if I double the radius, doubling the diameter will actually quadruple the area. It'll actually quadruple how much pizza we have. So instead, I need to consider which one of these is going to produce about double the amount of area. So if we real quick think through here, A equals pi r squared for a circle. So that's pi 10 inches squared, or excuse me, 5 inches squared. My apologies. Radius squared. So that would be 25 pi square inches. So if we think through the rest of these, if I have a diameter of 12, that would be a radius of 6. So 6 inches squared would be 36. Well, 36 isn't double 25. If I take B, it's 14, so 14 is the diameter, then the radius would be 7. So 7 inches squared would be 49 pi square inches. Well, actually 49 is really close to double 25. It's just one off. So let's just check 16 real quick. So if 16 is the diameter, 8 would be the radius. So if 8 is the radius, then we square it, we get 64. No, that's not closer to double 25. So it must be the 7 inches, which will produce a 49 there. So my answer is B. The answer is B, because, actually we don't need a decimal there, or a period there. We're going to write a sentence. B, because the area of the 10-inch pizza is 25 pi square inches, and the area of the 14-inch pizza is about twice that, at 49 pi square inches. And that leaves us with H. I'm going to come up here and just kind of split this space here. H. A 6-inch diameter balloon holds a pint of water. How much water does a 6-inch radius balloon hold? So we're going from a 6-inch diameter to a 6-inch radius. So if we were to change those both into diameters, or change them both into radii, then we can get our scale factor. So my scale factor K here is going to be, let's just change them both into radiuses, because that's what we're going to be, well, it doesn't really matter. We'll just change them both into radiuses. So for the bigger balloon, I have a 6-inch radius. For the smaller balloon, I have a 3-inch radius, which means we have a scale factor of 2. So therefore, how much is the larger balloon going to hold? Well, it's going to hold the 1 pint times our 2 scale factor, but pints, remember, are related to volume. So my scale factor is going to be cubed. So that'll be 1 pint times 8, or 8 pints. And that, ladies and gentlemen, is our lesson.